Okay, so today we take everything is a whirlwind tour, so we take a whirlwind tour through the striatum. And so what I'm going to do, first we'll talk about where is it, where is it, and then then talk about a simple diagram, sort of like that's easy, that's relatively easy to remember about how it basically works, and then I'll talk a little bit about how the cells work in the striatum, because they have a characteristic thing going on there called up and down state. I'll talk about that a little bit, and then I'll talk about a good diagram. You don't have to remember the good diagram, but just to sort of put it more into actual perspective of what's going on. So the striatum. So sometimes it's called the basal ganglia. So it's just ganglia is a sort of collection of cells. And various things are included in this, so it's not always exactly the same set of things, but when we talk about the forebrain striatum, what we're talking about is if you follow the neural tube up, it branches into a Y. So this is the ventricle here. So the ventricle branches into a Y, and then we can divide this into basically three parts on each side. And the three parts, the top part is what forms the cortex. This middle part is the septum. So this guy is the septum, this one. And the one that we're interested in now is the quarter that's on the underside and the lateral side, and that's the striatum. And striatum. And it's called striatum because there's a lot of fibers going through it, and striatum just means sort of lined. It's stria, it means like a line, and so it's got a line. Now, when you look at, if you look at a frog, it's a frog forebrain, just looks like a tube, and that's where the striatum is. No problem finding it. Now, if you know anything about human brains, you know it doesn't look like that. It doesn't look like that at all. So how does it get there? So if you look at a human brain, you basically got the cortex, and the cortex is kind of billowed out, and it's sort of, you've got like cortex on the top and cortex on the bottom. But where's the ventricle? So the ventricle is like sitting right here, like that. And here's the other ventricle on the other side. So that's the ventricle. So ventricle. So that's the same thing as that original hole there. Let's do a red one on that. So ventricle. So that's the ventricles right there. So where are the other parts? Well, the septum is there. It's just a little thing like this. It's about how big it is. And it's where you'd expect it. It's on the medial side, the inside of the ventricle. And then where is the striatum? Well, the striatum, so typically we'll have some thalamus there, and then the striatum is kind of sitting, somewhere out like this. So it gets completely sort of overgrown by the cortex, even though, like I said, it's really the lateral, ventral. So the stomach side, lateral side, quarter of the neural tube. So this is the striatum. Now that's the forebrain striatum. Sometimes people lump in, other parts into it, like the substantia nigra, and they sort of stick that in the striatum. We'll see why they sort of do that. But forebrain striatum, it just comes from there. So that's where it is in the. And then, so one of the other things that is sometimes lumped in there is if you go into the midbrain. So here's the colliculus, and you go down to the bottom of the midbrain, and there's a structure down there called the substantia nigra. So let's put the other one in. It's a pretty big structure. Sometimes that's lumped into the striatum. It's in the midbrain, actually. So it just means the black substance. substantia nigra. My students in previous years sometimes call it the substantia niagara, but it's the substantia nigra. And so this, it's got two parts to it. There's a part that has dopamine and a part that has GABA. So the dopamine part is called compacta. The pars compacta, and the GABA part is called the reticulata because it's sort of more net-like. Reticulata. So they're completely different functions, different parts. It's almost like two. And only the dopamine part is the black part. The reticulata isn't even black. So, but that's very closely connected to the striatum. Now, one of the problems, if we had a whole separate course to look at brain sections, one of the problems that you come in when you look at brain sections is, say you have two parts of the neural tube like this. And say the junction between the two parts isn't completely flat, like not a plane. So what happens is if you cut a section like this, what are you going to see if you actually, look at that section? If you look at that section, you're going to see, say this is the forebrain here, and this is the thalamus. So what are you going to see? You're going to see some thalamus sticking out the side. So here's some thalamus, and then you'll see some forebrain, and then you'll see some thalamus again. So there's the midline. So you'll see thalamus there and forebrain there. But say there's a different shape. So say the thalamus comes up, and say the thalamus sort of bulges up a little bit, and then so they're still topologically they're the same. We've got like the forebrain part of the neural tube, and we got the thalamus part of the neural tube. But if we cut a section through that, if we cut a section right through here, now it's going to look completely different. So now what it'll look like, you'll have some forebrain out here, and then you'll have some thalamus in the middle, and then some forebrain. So this would be forebrain on the outside. That's kind of the way it is actually. And then we got thalamus here. So the bottom line is that exactly what when you cut just a plane through something that's kind of curvilinear, you end up with, you could have the forebrain outside or the forebrain inside, but they're still sort of in this order of thalamus followed by forebrain. But that's one of the confusing things if you actually look at a lot of sections. Eventually, after you've punished yourself by looking at thousands of sections, it's just second nature, and you just have a three-dimensional picture of how all these things relate in your brain. But when you first look at a section, it's just like, I can't make any heads or tails. It's got some midbrain in it, and it's got some forebrain in it, and thalamus, just a mess, So just keep that original sort of segmentation of the neural tube in mind at all times. Okay, so that's kind of where it is. And what does it look like if we sort of zoom in on it a little bit? Let's just zoom in on this guy a little bit. It has something like sort of the caudate and putamen. And so if I draw, if here's the midline. So you got the caudate and putamen, but the caudate and putamen has this big bundle of fibers going through it. So there's this big fiber bundle here. And what's in there, it's like stuff coming in and out of the thalamus going up to the cortex. So there's this big fiber bundle. And I mentioned that if you look in rats, the fibers just break up into a bunch of small bundles throughout this entire structure. And what is that structure? That structure is, this part is called the caudate. And because that just means tail, because it has like a little sort of slightly tail-like structure. And this part is called the putamen. Putamen. but they're the same thing. And so in a rat, it's just called the caudatoputamen because it's just one kind of thing. And then if we look off to the side, there's another piece here called the globus pallidus. And so this is another colorful name. What does that mean? The pallid globe. And what is pallid? Pallid just means pale, so the pale globe. Now, if you look at a brain section, it doesn't look like a globe. It should have been called the globus trapezoidus or something like that because it's kind of sort of trapezoid shape. And then if you look, there's another fiber bundle sort of under the globus pallidus, and then there's a couple more structures that we'll talk about below that. They're smaller than this, but I'm drawing them big enough so I can put the names in them. And these are the nucleus accumbens. And what is that's a great name. That means the reclining nucleus. So it's just reclining underneath the rest of the striatum. And this guy is called the ventral pallidum. So those are some of the ones we'll talk about. So the caudate and putamen, basically the same thing, but just separated by this bundle. The globus pallidus, the putamen and caudate project to the globus pallidus. Then you've got the sort of a parallel set of things, the nucleus accumbens and the ventral pallidum. Okay, so what we'll do to start with is make a not very good diagram of the striatum, but it's one worth remembering because it kind of lays out kind of the main parts. And it turns out the striatum, meaning the caudate putamen and the nucleus accumbens part. I should draw this here. So this guy comes out of here and expands. So these two parts here essentially receive input from the entire cortex, all of the cortex. Every single area in the cortex goes to some subpart of the striatum. And so there's a bunch of different parts of the striatum, but let's just artificially divide them into sensory striatum and limbic striatum. So we'll start off with sensory striatum, and then limbic striatum over here. And so what are the sort of basic connections? So if we start at sensory cortex, start over here, sensory cortex. So, say area MT or area MST. So sensory cortex, projects down to the caudate and putamen, and so we'll make those guys caudate/putamen because they're kind of the same thing. And if we look at that projection is an excitatory projection. So the sensory cortex excites the cells in the caudate and putamen. And then the caudate and putamen projects down to the globus pallidus. The pale globe. And that's an inhibitory projection. So the cells in the caudate and putamen are inhibitory cells, and they inhibit the globus pallidus. And then the globus pallidus projects down to the thalamus. Now, if you actually look at it in a section, it looks like it's kind of going up, because of this business over here. But in terms of the neural tube, the sensory cortex, caudate and putamen, and globus pallidus are part of the forebrain, and the thalamus is part of the thalamus. And so it's a downward projection relative to the neural tube. And that is also a minus. That's also a minus. So there's two minuses in a row, and we'll talk about what the relevance of that is. But then eventually, the thalamus goes up to motor cortex, So the thalamus goes up to motor cortex, and then the motor cortex, comes back out to the spinal cord. And so that's how we can get a movement out. And there's two other structures that we'll talk about that have projections back and forth. And so one of them is the substantia nigra. Substantia nigra. There's two parts of it, and so we'll just leave it unsubdivided for now. And then there's another structure called the subthalamic nucleus. We'll put that down in the thalamus here. Subthalamic nucleus. And this guy goes to the globus pallidus and back. And in particular, this connection is a positive connection here. Okay, so that's our, how many parts? So 1, 2, 3, 4, 5, 6, 7, 8. I got up to 8. Okay, but that's a reasonably small number. Now, all of these things have other inputs. So motor cortex, has a lot of other inputs. It gets input from premotor cortex and other parts of the thalamus. It gets ascending inputs of all different kinds. And, the thalamus has all different kinds of other inputs also, which we haven't drawn. But let's just look at this circuit and just try to sort of reason about some of the basic problems that you get with damage to the basal ganglia, like Parkinson's. So if we look at this, what we see is that this connection right here serves as a gate, because this globus pallidus is inhibiting the thalamus. So stopping the thalamus from doing stuff. So maybe somebody else in the cortex said, I want to grab that thing. I see something out there using my visual cortex, and I'm telling the motor cortex to grab that thing. The globus pallidus says, no, sorry, you can't do, no, can't do. We're turning you off. And so the way that the striatum controls movement is by somehow shutting down the globus pallidus so that a movement can come out. And so if you look at what happens in Parkinson's, is the dopaminergic cells die. So you got dopamine here and GABA. So the dopaminergic cells die. When they die, their projection up to the cauda imputamen causes damage to the cauda imputamen cells. So the actual initial sort of onset of problems is the dopamine cells are dying, but the cauda imputamen starts to die because its input is not working right. And so let's just reason about what happens. So what happens is these guys are getting excited by the cortex. Now they started to die off. As they start to die off, they don't properly inhibit the globus pallidus, because these guys are inhibiting the globus pallidus, which is inhibiting the thalamus. And so what does that mean? That means the globus pallidus is going to be too active, not inhibited enough. And so the result is the thalamus will be too inhibited. So the globus pallidus is too active and the thalamus is not active enough. And so what does that do? It stops movement. And so what does a Parkinson's patient look like? They have real trouble starting a movement. And if they actually get going, like if you paint a stripe on the ground and so there's a strong sensory stimulus to get them going, they might be able to get going. And then when they go, they have trouble like stopping, like they're in the walking program and then might run into a chair or something because they're having trouble sort of transitioning the motor program into another branch. So what are some of the therapies where you can sort of stick some more dopamine in there? That helps a little bit, not very much, makes you kind of a little crazy. Gambling causes gambling problems. You can burn a hole in the globus pallidus. That's another thing you can do. It sort of seems like a kind of a harsh way of doing it, but if you actually stick an electrode in and literally burn a good-sized hole in the globus pallidus, that will actually can sometimes help a Parkinson's patient, because there's all this other input to motor cortex that can cause movements. It's just being shut down by this gate that just says no movement. And we saw a similar thing in the colliculus, and the basal ganglia projects to the colliculus also. where, I could look at that, I could look at that, I'm just looking straight ahead. Now there's something I might look at, and I might look at that, I might look at that, and then the basal ganglia can kick in and say like, okay, now you can just look at that one. Same way with movements. Like you're programming movements all the time. I might want to pick up the paper clip, but or maybe I'm going to pick up that. Maybe I'm going to touch the board, but don't do any of that. Just sit here. And then finally I decide I'll pick up the paper clip. So that's just the gross sort of anatomy of a problem with the basal ganglia. And if you want to read, there was these ne'er-do-well guys, it's always guys, who are up in the PTP, up in San Francisco someplace, and they're trying to cook up some synthetic heroin. And they accidentally made this instead. It's a compound, MPTP. And they took it, and they woke up the next day completely unable to move. They had just completely burned out their caudate and putamen with a chemical. And so the suggestion, and this happened quite a number of years ago, and so neurobiologists said, great, now we can sort of make Parkinson's animals because they could sort of like have a chemical that specifically damages the caudate and putamen without messing around with much else. It also made it pretty clear that the caudate and putamen is pretty sensitive to things like pesticides or combinations of chemical pesticides, which probably is partly responsible for Parkinson's. The other thing that's responsible for Parkinson's is that you can just view it as like inability to take out the garbage. So Parkinson's, you start to build up this protein called alpha-synuclein, and that protein, it's a protein that's supposed to be there. It's a protein in synapses that's supposed to be there. But as your physiology ages, and if you eat too rich of a diet, your brain cells can have trouble taking out the garbage. And so alpha-synuclein starts piling up and causing trouble, very similar to Alzheimer's. So, and then if you've got some pesticides in there too, it's really hard on the caudate and putamen. So that's kind of the overall picture, this gross overall picture. And what about I put the subthalamic nucleus up there. What would happen if we just blew out the subthalamic nucleus? So then what's going to happen is the subthalamic nucleus excites the globus pallidus. So that's going to make the globus, if you remove the subthalamic nucleus, the globus pallidus is not going to be excited enough. It's kind of the opposite of Parkinson's. And so what's going to happen is the gate is going to be too open. And what happens with people with a subthalamic nucleus lesion is they're kind of constantly making these weird arm movements that they can't, it depends on what part of the subthalamic nucleus you hit with your stroke, but they make these weird movements or reaching movements. It's kind of like, it's probably what your brain is planning to do all the time. It's like, I could grab that. No, but don't. It's like, there's a hot burner. Don't touch that. So these movements get released because the gate is too open, because the subthalamic nucleus is not there and exciting the globus pallidus to shut everything down. So those things they're not really diagnostic, and they're just like gross misperformance of the system, because you just have way too much inhibition or not nearly enough inhibition. They don't really tell you how it works. They just kind of tell you how does it fail when something like completely gets shut off and this thing is way too low activity or way too high activity. Now, there's another parallel path. There's like about 6 parallel pathways, but there's another parallel pathway if you look at limbic neocortex. That projects down to the nucleus accumbens, the reclining nucleus. And that's an excitatory projection, just like it is here. And then we have an area that's like the substantia nigra called the ventral tegmental area, VTA just for short. And that has dopamine cells. It doesn't have GABA cells in it, but it has the dopamine part. And that projects back to the nucleus accumbens. Nucleus accumbens projects down to the ventral pallidum, which is like the globus pallidus. And then this thing goes down to a structure that you probably haven't heard of called the pedunculopontine nucleus. I didn't even mention it in my... And that thing goes to the spinal cord. So that's yet another major motor output pathway, which I didn't mention when I were talking about the motor. I'll make when I talk about the limbic system next week, I'll make a diagram of what's connected to it. So pedunculopontine nucleus, it gets a lot of other inputs besides just this one. But you have the same kind of a gating thing going on here. So this guy is another gate from the ventral pallidum that can gate the activity. So this guy's inhibitory and inhibitory here. So you have a parallel set of structures here that have that same kind of signed structure for sort of gating actions that are caused by the pedunculopontine nucleus. Yeah. Oh yeah, so I'll write that out. So it's a very generic name. It's just ventral, which means on the stomach, tegmental, which also means on the stomach. That means floor. Ventral tegmental area, very generic meaning, but it's a cluster of dopamine-containing cells that projects into the nucleus accumbens. Okay, so that's our basic picture. So now let's talk. Let's zoom in a little bit and talk about the physiology of the basal ganglia. And so there's a very characteristic behavior of the cells, of the main cells in the caudate and putamen, that we have some idea about how it works. And so what this behavior is called the up and down state. So now if we zoom in. So it's called the up and down state. And so it turns out this occurs sometimes in the cortex too, but was first really recognized very clearly in the basal ganglia. And this is in the main projection cells of the basal ganglia. And so these main projection cells are called medium spiny cells. So they have spines on them just like pyramidal cells do, but the difference is they're inhibitory. So medium spiny cells in caudate and putamen. These are the ones that go bad when you get Parkinson's. So if you look at these medium spiny cells, and this occurs even in a dish. So you can get a little chunk of the striatum and stick it in a dish. So the cells might be quite inhibited, like say around minus 90 millivolts. So, and say here's like 65 millivolts, minus 65. So, and then what will happen is you'll see the cell will just sort of pop up to about 65. It won't spike necessarily. But when it's in that up state, it's capable of spiking. So it may or may not spike when it's in the up state. And then you'll see it pop down, and it never spikes in the down state. So this is, basically up. So it's so these experiments have to be done intracellularly, and so it's hard to do them in an actual animal without a slice, because it's hard to put an electrode into a cell and just record inside the cell. There's various optical ways that people have developed more recently, but in general, most of this work has been done in just like a slice in a dish. So we know less about how it's all related to the rest of the circuit, but at least we know something about how the cell works. So what is causing this? So an idea for what's causing it. So obviously one thing that could cause it is you could just turn on a bunch of inhibitory synapses and then shove the cell down and then turn them off and the cell floats up and then it's spikeable. But there's another thing which is a particular kind of a channel that has a strange behavior. So if we remember when we talked about the delayed rectifier, so delayed rectifier. So that was the potassium current that puts everything, rectifier means put everything right. And so the idea was, here we're at minus 70, the spike goes up, that's the sodium current, and then you get some delayed rectifier. And the delayed rectifier helps kind of shut the spike down. So that's the delayed rectifier there. It's a potassium current, is an inhibitory current that will sort of put everything right. The spike will stop because the sodium channels got inactivated, but then in addition, you start opening the potassium channels and they help put everything back. So that's a regular rectifier. So what they found in the basal ganglia is called the anomalous rectifier. So an anomaly, So an anomaly is sort of a wrongly named, that's what anomalous means. Sort of like a wrongly named rectifier. So it's a rectifier, it's a potassium current, but it's a potassium current that is activated by hyperpolarization. Hyperpolarization. So that's backwards, because what is this guy? This guy is this guy. So it's K plus. It's a K plus potassium current. So this guy is activated by depolarization. Activate by dipole. So the delayed rectifier, when you're just sitting there, the delayed rectifier isn't on. It only comes on when you depolarize the cell. And when the sodium current depolarizes the cell, then it turns this guy on, and this guy sort of puts everything right. But this is the exact reverse. So this is something that when you hyperpolarize the cell, so if the cell is slightly depolarized at minus 65, this current is off. And if you hyperpolarize the cell, say some other guys come in and push the cell down, if it gets negative enough, this current will come on. But what does this current do? It shoves it down even more. So you can sort of think of it as like a little switch that will shut the cell off and stop it from being able to be activated. So that's the anomalous rectifier. And we know that those currents occur in these medium spiny cells. It's kind of like the spike current. The spike current is a positive feedback situation. When the sodium channels open up, they depolarize. When the cell gets depolarized, it causes the sodium channels to open up. And so it just goes, it's like lighting a fire, and then you get this rapidly rising spike. This is the same thing in reverse. If you're somewhat depolarized, it's not on, and if you start pushing down, suddenly it goes wham, and shoves it off, and then stays on, stays open. So that's a behavior. So how is that related to, how we think the basal ganglia works? Well, one idea is that maybe this is a way of sort of switching circuits in and out of enablement. So the idea is that you've got some connections that come in and say, we're going to enable all these parts of the basal ganglia that are involved for the walking movement. They're not going to actually make the walking movement. What they're going to do is just say, we've switched off all the cells that don't have to do with walking, and we've got the cells switched on that do the walking pattern. Now you can do your walking pattern. And then similarly, you could have some other pattern, like if it's a cat, like the little bat the prey item pattern. So you'll just switch on the bat the prey item circuits, and then you can actually do the batting the prey item, which itself is complicated. It involves a bat, and then you have to back up, and then another bat. You've got a whole series of patterned things to play out. But that's the suggestion of what's going on here, is that it's the basal ganglia is involved in kind of switching circuits in and out of use. Because like you're walking along, everything's going good, you're doing the walking pattern, now we got to make a turn. So now you sort of like switch into the turn pattern. And this applies at the level of like a single step or just a couple steps, all the way up to very long-term goals. And when we look at the actual sort of overall connections in the striatum, if you've got the striatum down here and you have the cortex up here, the kind of connections you get are kind of sort of going to different places. So like some part of the cortex will go down to a part of the striatum, and that will come back up and go to a different part of the cortex. And like same over here. So you're in this part of the cortex, you go down to this part of the striatum, and when you come back out of the striatum up into the cortex, through these pathways from the thalamus that go back up into the cortex, you go to a different place. And so the idea is that you have some kind of hierarchical temporal control of behavior. And I mentioned this before, like, if you have it in your mind, like, I'm going to make some dinner, that's kind of a long-term goal. It's going to take an hour or so to do it, depending on how elaborate it is. And so you've got the goal state of, I'm getting ready to make dinner. And so some part of the striatum might switch on the, I'm getting ready to make dinner guys, and keep them on for like an hour. And then when they're on, then you can play out all different little things, like chopping up the onions. That's like a separate little program that we release. That only takes like a minute or something. But we've got that other up state keeping the goal of making dinner on the whole time. And so that's really a general sort of feeling for what the striatum is doing. It's doing this segmentation of behavior at different hierarchical temporal levels, because we have long-term goals that last an hour, other ones that maybe take like 5 minutes, other ones that maybe take only like 500 milliseconds. So we can see modulation of parts of the caudate and putamen that are related to hand movements that are happening very rapidly at the level of, like once every half a second or a quarter of a second. In addition, we see these much longer term things, especially as you get into the nucleus accumbens. Okay, so what's a very simple task that people have done particularly with Parkinson's patients, that sort of illustrates this kind of idea. And so let's start off with something easy for Parkinson's. And then here's hard for Parkinson's. Just to give some idea of these things just made very concrete. So say you have two displays. You have one display, but there's two different states that the subject, like a Parkinson's patient, has to learn. So they have to learn, program 1. When they're in state program 1, they have to do one thing. If you say, okay, now we're doing, part 2, program number 2. And so program 1, so what is the task? The task could be either to point or even just look, because we'll see that the basal ganglia is heavily involved in controlling saccades. So you got a bunch of letters up on this screen, like A, B, C, D, E, F, something like that. And they're always up on the screen. A, B, C, D, E, F. So if you have them do a task where they have to look or touch, A to B to C, and then D to E to F, that one they can do. And then if you switch them over to program number 2, which is, sorry, I put them in the wrong side. Sorry about that, guys. So you switch them over to program 2 where they have to do this. They can switch back and forth between those two programs easily. Now, they might not even be using the basal ganglia that much. So that's one thing to always consider here. There's more parts of the brain than the basal ganglia. There's more parts of the brain that can do segmentation of behavior than just the basal ganglia. The basal ganglia is really good at it, but there's other parts. And so they might be using other parts of the brain to do this task. But what's hard for a Parkinson's patient? It's very hard for a Parkinson's patient to switch between programs that have a common element. So if so we have the exact same letters before, A, B, C, so it's not conditioned by just the difficulty of parsing the visual display. But the only difference is that program 1 and 2 have an overlapping element. So in this case, we have, when you're in program 1, you do A, B, C, and when you're in program 2, you do D, B, F. So that's very hard for Parkinson's. So again, why is it hard? Well, it's because when you get to that, so there's several ways to skin a cat, so to speak. So there's several ways. You could say, like, I just know I got to go to B after A. And I don't care about anything else. I just know that A goes to B, and then when I'm on B, B goes to C. You can't use that simple strategy in this case. In this case, you have to know I'm in program number 1, and program number 1 is ABC, the whole thing. And program number 2 is DBF, the whole thing. And so Parkinson's would have trouble with this because of this overlapping element, because you can't use the strategy of, if I'm at A, just go to B and forget everything else. So that's something that's very easy to demonstrate behaviorally that shows that the basal ganglia may be involved in this set, sort of a set for a whole sequence of events that occurs. Like program 1, there's this whole sequence. It's not just going from A to B, it's going from A to B to C. Okay, so that's a simple task that is particularly damaged by having damage in the cauda imputamen. Okay, so for the final bit, let's just look at the whole thing, because I didn't do it. This is not a very good striatum. You need like a real striatum. So you don't have to remember this one, but we always like to just occasionally back out and just make sure that we have some appreciation for the whole problem. So what do you have in the striatum? Well, there's maps in the striatum, just like elsewhere. So let's just take like the cauda imputamen. Like if this is the cauda imputamen right here, CP/P, and here's the globus pallidus. What do the cells in here look like? Well, the first thing is there's 2 parts of the globus pallidus, completely different from each other. So this one's called the globus pallidus external, because this is the midline over here. And this one's called the globus pallidus internal. But it's even more than that. So if you just go in and inject a single cell here, there's a little cell. It's a medium spiny cell, the same kind that has the up and down. What does that look like? Well, it sends an axon out here, and then it makes a little terminal, and then it goes and makes another little terminal, and then it goes, makes another little terminal, and another little terminal, and then it goes down to the substantia nigra, because that was one of the connections. The substantia nigra projects up to the cauda imputamen, and it also, I'll write cauda imputamen out. It also projects, the cauda imputamen projects back to the substantia nigra. So this is caudate putamen. But it turns out there's actually a map in there. So if we go and get another cell nearby, this guy will sort of go in there and project over there, a little bit over, and a little bit over, a little bit over. So there's actually 4 maps in the projection from the caudate putamen to the globus pallidus, and then there's more maps when you get down to the substantia nigra, because it projects in a map-like fashion to the substantia nigra. So it's maps all the way down. And one of the reasons, like you often think about the substantia nigra of the striatum involved in reward, and I always say, like, if your index finger did something wrong, don't punish the middle finger. It's only the index finger that needs to be punished or rewarded. So you need a lot of sort of spatial structure to all these things. And this is sort of approximately the actual size of the actual axon terminals there. Okay, so let's make a nice big, start with sensory cortex here. And we'll show how the whole eye movement system is kind of worked in here. So we've got motor cortex up here. And we'll put premotor cortex here, so we'll make... So an example might be the frontal eye fields. That's involved in sort of controlling eye movements. And let's just put little subdivisions in here, sort of midbrain and thalamus. So this is forebrain up here. And this is thalamus and midbrain. Okay, so we see that all these parts of the cortex project to the caudate putamen. So here's caudate putamen. So all these guys go there. So sensory cortex goes there, motor cortex goes there, premotor cortex goes there. And then there's a projection down to the 2 parts of the globus pallidus. And now we have to distinguish these because they're actually quite different from each other. So here's GPE and GPI. So that's internal and external. Okay, so there's these 2 guys here. And so the caudate putamen projects down to that. It also, goes all the way to that one, and then this one projects to that too. So that starts to get kind of complicated because you got like minuses. There's minuses on minuses on minuses. And then, so this, if you look in the literature, this guy is called, this guy here is called the indirect pathway. Put that in blue so we can see that. Indirect. So if you read any literature on the basal ganglia, you got the indirect pathway, and this one here is the direct pathway. Okay, so now let's get a few more inputs. So another big input to the caudate putamen, which we'll talk about when we talk about place cells, is entorhinal cortex. You probably weren't expecting that one. So entorhinal cortex, that's hooked up to the hippocampus, or a lot of people consider it part of the hippocampus. So that guy is a strong projection from the entorhinal cortex into the caudate putamen. So not just neocortex, but also these other sort of cortices that are down, that have simpler layer structure. Okay, so what about the substantia nigra? So let's put that in next. And so it's down in the midbrain. So we have the substantia nigra compacta. That's the dopamine part. And then we have completely different connections from the substantia nigra reticulata. That's the GABA part. So here's those two guys. So the and then we got a couple things in the thalamus. So why don't I just put all the structures that I'm going to put here. So then we also have the amygdala, because we want, we're interested in the amygdala because, for fear and other things like that. We know that that's involved in basal ganglia actions. And then we have the thalamus here, like the ventral thalamus that goes up to motor cortex, and the ventral anterior thalamus that goes up to prefrontal. So this is mote, prefront. So we got that guy, and then we got the subthalamic nucleus, STN, and this is ventromedial and involved in eye movements. Eye move. And then we have subthalamic nucleus. What is that? We just call it lateral. Subthalamic nucleus lateral. And that guy's involved in skeletal muscle. So like more body stuff. And then we got the lateral habenula. That's a big projection. Lateral habenula. That's part of the epithalamus. Remember the top of the thalamus? The dorsal thalamus, that would be like the lateral geniculate, but the habenula is that top part that's hooked up to the pineal gland. And then last but not least, the superior colliculus. So the superior colliculus, it has a big basal ganglia projection. Okay, so did I get everybody? Globus pallidus. Okay, got everybody. So now we'll just connect up a few extra things. So the dopaminergic part goes up to the cauda imputamen. So that's the one I had before. And it comes back down to the dopaminergic part like that. And there's also a projection that goes separately to the substantia nigra reticulata. That one doesn't project directly back like the dopaminergic one does. The way that the gating occurs is basically here. So this is our gate. So we had the gate before. Remember, that's the thing that's gating the thalamus. But there's another gate, and this is one of the reasons why some people slap the substantia nigra in with the striatum, because this guy also. So the GABA part of the substantia nigra has a big projection into the thalamus, and so that's another gate. It's another way that it's kind of in the same position. So the GABA part of the substantia nigra is kind of in the same position as the GABA part of the globus pallidus internal segment, and they both have this sort of gating action on. So gating action on the thalamus, because how does the thalamus get out? It gets out by essentially, going up to, going up to motor cortex, right? So it goes up to motor cortex. So motor cortex can actually come out and go down to the spinal cord. So that's our final. Make sure we got the final common output pathway here. So spinal cord to make a movement. Okay, so the globus pallidus can gate the thalamus being able to move, but the substantia nigra reticulata GABA part, which is kind of like the globus pallidus internal segment GABA part, can also gate the thalamus. Okay, so So we have also a projection from the lateral habenula down to the dopamine part. So that's more rewardy kind of things going on, or fear, sort of fear and rewardy things going on coming from the amygdala and the lateral habenula, getting into the dopaminergic part, which gets up to the caudate putamen. And then we've got the subthalamic nucleus, which remember was hooked up. And so the subthalamic nucleus is hooked up to this, back and forth to this external segment, but it doesn't have a projection to this globus pallidus internal segment. It's mainly sort of involved in this indirect pathway. But then recently, what people found is there are all these things that project down to the subthalamic nucleus from the cortex. And so, like, motor cortex just goes, straight down to the skeletal muscle subthalamic nucleus. So that's kind of extra direct, and so that's called it's hyper complex. So that's called the hyperdirect pathway. Because, the cortex, it doesn't even have to go through the caudate putamen, it just gets immediately into the subthalamic nucleus, and it can sort of immediately get out and gate stuff. So here's the hyperdirect. Okay, and then last but not least, we have to hook up the whole eye movement system. So how does that work? Well, there's a huge projection from the substantia nigra GABA part that goes into the colliculus, and that's another gate. And I talked about that before, like if you're tracking something around and then suddenly you decide, I don't care about what I was tracking, I'm going to switch over to tracking something else, the substantia nigra will kick in and tell the colliculus, okay, it's okay to, start tracking something else. And so, eye muscles, like I said, not just eye muscles, but neck muscles and things that, change where your gaze are, that's like about a third of your motor system. So that's a big additional pathway. So I think we got most of it in there. So that's a better striatum. This is like the main sort of actors in the striatum. So, obviously there's a ton of input coming into motor cortex that I haven't drawn here, and a ton of input coming into sensory cortex. Motor cortex goes over to somatosensory cortex. These guys are connected up. There's like a zillion connections to premotor cortex I didn't draw. So this is still leaving out 90% of the connections, but it gives you some idea of the basic architecture, that you have this basal ganglia. It's having to do with sort of segmentation, temporal segmentation of behavior, and in controlling the superior colliculus, controlling eye movements, and controlling skeletal movements. There's one thing I definitely left out. Oh yeah. So we have to go from the eye movement guy down to the GABA part. So there's a lot of pathways in here that you wouldn't normally think of, like the frontal eye fields go to the subthalamic nucleus, go to pars reticulata, and control eye movements. That wouldn't have been one that would have come to my mind, when I first learned neuroanatomy. So, but that's a very important pathway for sort of segmenting sequences of eye movements. So, okay. So any questions about the good basal ganglia? So if you read any literature on the basal ganglia, you'll hear all this stuff about indirect and direct pathway and hyperdirect pathway, which was kind of discovered a little later. It was discovered that like the subthalamic nucleus gets all this cortical input. It's all mapped. All different parts of the cortex go to different parts of the subthalamic nucleus. And so somehow this is all coordinated. Like when you're doing anything, like all these things are doing their things. And it's I don't put this up to say that, we understand how it works. We just have some generic idea that there's some gating going on, and this stuff's all coordinated, and there's dopamine involved and GABA involved. But I put it up mainly to make you be skeptical when somebody says, I think this is how the basal ganglia works. You feel like, wow, what about the lateral part of the subthalamic nucleus? You haven't put that in your diagram. So, okay, so people overwhelmed with the good high quality basal ganglia. You can go back to the original one, which is easier, just like cortex goes to cauda imputamen, goes to globus pallidus, goes to the thalamus, that goes to motor cortex, goes to spinal cord. Remember that one. Okay. Any other questions about? Yep.
Just real quick, when you were talking about like a subthalamus nucleus lesion in sort of like the ocular carcasses, I think I just missed it, but were you saying that the thalamus would be overactive and the globus pallidus would be underactive?
Yeah. So if you lesion the subthalamic, so just a gross lesion that just like wipes out like the subthalamic nucleus and a bunch of other stuff around there will essentially, it gives you something called hemiballismus. It just means like, something that's happening to one part of your, so this is, STN, subthalamic nucleus lesion. So it just means ballistic movements that you can't control that happen on one side of your body. And so what is the problem there? Well, you're not exciting some of these globus pallidus inhibitory guys enough. And so the end result is that this gate is too open. So if the gate is too open, then all the different parts of your brain that are planning to do stuff but are normally sort of allowed to plan and do stuff without actually having it get out. So I think that's an important point, is that what your brain is doing, your brain neurons are pretty slow. And so what it's doing is, in parallel, it's planning to do all these different things, basically getting set up to do all these different things. But then you've got a sensor that says like, nah, you can't do it until I decide that you do it. And then when that sensor releases, then you can do the action at the appropriate time. But if you screw up the gate, you're going to start getting some of this planning type behavior leaking through and actually generating output. And you could easily imagine various kinds of pathological conditions where something like that might happen in somebody who has all their connections. If the balance between some of these things isn't quite right. And they can sort of release behaviors that they should just think about and not actually do. Okay, any final questions? I think we'll end the recording there, Stan.